Welcome back to Trig Part 3 notes. Today we're going to start with the fundamental trig identities. These are really important, especially for future calculus classes, so I would make sure that you know them. The first set is the reciprocal identities, which you already know. Sine and cosecant are reciprocals of one another, cosine and secant are reciprocals of one another, and so are tangent and cotangent. The next group is the quotient identities. Tangent is sine over cosine, and cotangent is cosine over sine. The next group is the Pythagorean identities. These are incredibly useful. The first one is sine squared plus cosine squared equals 1. That comes right from the definition of the unit circle. If you look back at the definition of the unit circle, which is the circle of radius 1 centered at the origin, the equation for the unit circle is x squared plus y squared equals 1. Well, x is the cosine of the angle, and y is the sine of the angle. So x squared, replacing x with cosine, would give you cosine squared, plus y squared, replacing y with sine, would give you sine squared, equals 1. So that's where cosine squared plus sine squared equals 1 comes from. And the other Pythagorean identities actually come from the sine squared plus cosine squared equals 1. If you were to take this entire equation and divide everything by the cosine squared, right? You can do whatever you want to an equation as long as you do it to both sides. So if I divide the entire left-hand side by cosine squared and the entire right-hand side by cosine squared, I would have sine squared over cosine squared, which would give me tangent squared, plus cosine squared divided by cosine squared would give me 1, equals 1 divided by cosine squared would give me secant squared. And the other Pythagorean identity comes very similarly. If we take the entire sine squared plus cosine squared equals 1 and divide everything by sine squared. Sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared, equals 1 divided by sine squared is cosecant squared. The confunction identities are important as well. If you see how we have these two angles, we have pi over 2 minus x and x. Pi minus 2 minus x here is going to give you the complement of x here. So if you look at your unit circle here, pi over 2 or 90 degrees minus 30, that would give you 60 here. So the sine of 60 equals the cosine of 30. So the cosecant of an angle is equal to the secant of its complement. And the tangent of an angle is equal to the cotangent of its complement. And the even and odd identities we've talked about before as well. Sine, tangent, cosecant, and cotangent are all odd, which means that the sine of the negative angle gives you the opposite of the sine of the positive angle. Same for the other three. And cosine and secant are even, which means the cosine of the negative angle is the same as the cosine of the positive angle. Same for secant. So let's do some examples using these fundamental trig identities. The first example we'll use the fact that we know that the tangent of theta is equal to 2, and we know that the cosine is negative, we can find all 6 trigonometric functions. Well, just knowing one trig value and one little characteristic of another trig value is enough for us to be able to get all 6. Well, let's look at tangent. Tangent is equal to 2. 2 is positive, so that tells us that that angle, theta, must be in quadrant 1 or quadrant 3. But this is saying, hey, cosine is negative. Well, since all trig values are positive in quadrant 1, we must be in quadrant 3. So when we know that tangent and therefore cotangent will be positive and the rest will be negative. So tangent was given to us. Tangent is equal to 2. Once you have the tangent, it's really easy to get the cotangent. That's just the reciprocal of the tangent, which is where cotangent equals 1 over 2 comes from. And so now what we want to do is look at these fundamental trig identities and come up with an identity that has one unknown and the rest known. So we can't use something like tangent is sine over cosine because we don't know sine and we don't know cosine. But look here, we know that tangent squared plus 1 equals secant squared. We know the tangent, 1 is 1, and we don't know the secant, so that gives us one unknown. So we'll say, okay, tangent squared plus 1 equals secant squared. We know the tangent is 2, so 2 squared plus 1 is the secant squared. 2 squared is 4 plus 1 gives us 5, so secant squared is equal to 5. So to solve for the secant, we can take the square root of both sides. But remember, when you take the square root to solve, you have to take plus or minus. So we get two answers, the positive and the negative square root of 5. Well, where are we? We are in quadrant 3. And we already discussed how in quadrant 3, only the tangent and therefore cotangent are positive and the rest are negative. So the secant must be negative square root of 5, which is where this comes from. And now we'll use that reciprocal identity that says the cosine is the reciprocal of the secant. So if secant is negative square root of 5, cosine must be 1 over negative square root of 5. And when we rationalize that, we get negative root 5 over 5. Now, to find, all we have left is sine and cosecant. Now, we could do cotangent squared plus 1 equals cosecant squared. That is a choice. But we could also now try to use that tangent of x equals sine over cosine and solve for sine. So if tangent is equal to sine over cosine, multiply both sides by the cosine, the tangent times the cosine will give us the sine of the angle. Well, the tangent is 2 times, we just found the cosine to be negative root 5 over 5. So that gives us the sine is negative 2 root 5 over 5, which I have here. And then the cosecant is the only one left. That's the reciprocal of the sine. So that's going to be 5 divided by negative 2 root 5, the reciprocal. When we rationalize, this should say the square root of 5. I multiply the top and the bottom by the square root of 5. Root 5 times root 5 gives me 5. These 5s will cancel, and I'm left with the cosecant being negative square root of 5 over 2. So that is the way to solve this problem using the fundamental trig identities. And I encourage you to try that just to get used to these fundamental trig identities because, as I said earlier, they are very important. But there is another way. Trigonometry comes from the Greek language meaning measurement of triangles. So you can turn this into a triangle. If the tangent is equal to 2, well, that's the same thing as 2 over 1. So if you draw a right triangle, label one of the angles theta, then tangent is opposite over adjacent, 2 over 1. Then you can use this Pythagorean theorem, or the Pythagorean theorem, to say 2 squared plus 1 squared equals that hypotenuse squared, to get the hypotenuse is the square root of 5. I have no problem with you doing it this way. I still want you to practice these fundamental trig identities. The only thing I want to caution you about using this is you have to remember which quadrant we are in. This is a triangle, and these all represent lengths, and lengths are always positive, right? But when you're talking about the angle might be in a different quadrant where not all the trig values are positive. For example, here we're in quadrant 3. So before you do the triangle method, go through and say, okay, we're in quadrant 3, so sine, cosecant, cosine, and secant are all negative. Give them all a negative sign. Tangent and cotangent are positive, and then go ahead and fill in the rest using the triangles. Other things we can do in trig. So trig is really just fancy algebra. It's just taking what you know in algebra and just adding these new trigonometric functions to it. So you're going to have to trust your trig instincts here because trust your algebra instincts here because trig follows really closely to algebra. So whatever you would do if this was an algebra problem, follow those algebra instincts and try it in trig. So looking at this first one, simplify the sine times cosecant minus sine. When you see something like this, your algebra instincts are probably telling you to distribute. So let's do that. Let's distribute the sine to both. So we get sine times cosecant minus sine times sine, or sine squared. Well, when you get stuck, when you're trying to simplify things, you can always turn everything into forms of sines and or cosines. So when you get stuck, turn everything into sines and cosines to help with the next step. So cosecant is 1 over sine. Notice these signs are going to cancel, and I'm left with 1 minus sine squared. Well, this is a version of that Pythagorean identity. That Pythagorean identity that says sine squared plus cosine squared equals 1. If I subtract sine squared from both sides, I get that cosine squared is equal to 1 minus sine squared. So this 1 minus sine squared of theta is equal to cosine squared of theta. So when I simplified this trigonometric expression, it simplified all the way down to cosine squared. When you're simplifying, when you're verifying, this next example is a verify. This is another way of saying, hey, I want you to simplify, but I'm telling you what it's going to simplify to. So when you're verifying a trig identity, what you want to do is pick the more complicated looking side and simplify it to look like the less complicated looking side. Well, how do you know which side is more complicated? Typically, it has more trig functions, has addition and subtraction, or it has higher powers. So the idea is to pick the more complicated looking side, in this case the left-hand side, and simplify it just like we did up here, except we know that it should simplify to cosecant. So when I take the sine plus cosine of theta times cotangent of theta, if you're not sure what to do, what did I say? I said turn everything into sines and cosines. Well, cotangent is cosine over sine. So when I multiply this together, I have the sine of theta plus cosine squared over the sine. I'm trying to add things right here. One of them is a fraction. So in order to do that, I'm going to need a common denominator. This is really sine over 1. So I'll multiply the top and the bottom by sine. And I get sine squared over sine plus cosine squared over sine. Once the denominators are the same, I can add their numerators over that denominator. And that gives me sine squared plus cosine squared all over the sine of theta. Well, this is that Pythagorean identity again. Sine squared plus cosine squared equals 1. This gives me 1 over sine, which is cosecant. I was able to verify that this simplified down to this, so I gave it a big check mark. Let's do another verify. And again, what you want to do is follow your algebra instincts. So when you see something like this, something minus something times something plus something, you're probably thinking, oh, I should do that thing that my teacher taught me called FOIL. So everybody in the first group is going to get multiplied to everybody in the second group. So secant times cosecant, secant times 1, negative tangent times cosecant, negative tangent times 1. I'm stuck, so I'll turn everything into sines and cosines. This is 1 over cosine, 1 over sine, plus 1 over cosine, minus sine over cosine times 1 over sine, minus sine over cosine. Now, you probably notice that these sines are going to cancel, and we're left with this 1 over cosine. So when I do that, this positive 1 over cosine of theta minus this 1 over cosine of theta is going to cancel. And I'm left with 1 over cosine sine minus sine over cosine. I'm trying to subtract with fractions. I'm going to have a common denominator. So I'm going to multiply the top and the bottom here by sine. That gives me 1 over cosine sine minus sine squared over cosine sine. Once the denominators are the same, I can subtract their numerators over that denominator, and I get 1 minus sine squared over cosine times sine. What is 1 minus sine squared? That Pythagorean identity, it tells us it's cosine squared. And then this 1 cosine is going to cancel with one of these cosines, and I'm left with cosine of theta over sine of theta, which is cotangent of theta, which is what it was supposed to be. So I get this nice little check mark here. Other things you can do with trig is, just like in algebra, you can factor. So you're going to factor in trig the same way you factor in algebra. Start by trying to factor out the greatest common factor. Cotangent squared minus cotangent squared times cosine squared. They both have a cotangent squared, so I pulled one out. And I'm left with 1 minus cosine squared. Well, what's 1 minus cosine squared? That is sine squared. Simplify further, we can turn everything into sines and cosines. Cotangent squared is cosine squared over sine squared. Notice these sine squareds are going to cancel, and that whole thing simplified down to just cosine squared. Let's do another factoring. Let's factor tangent to the 4th of theta plus 2 tangent squared of theta plus 1. You can turn your trig functions into variables, and however it would factor in variables is how it's going to factor in trig. So you can replace tangent with x, and however it would factor in terms of x's, put back in your tangent. And so this is going to factor into tangent squared plus 1 times tangent squared plus 1. And you can always distribute it out and make sure we get what we started with to double check. Well, tangent squared plus 1 should look familiar to you. That's secant squared. And tangent squared plus 1 again is secant squared. Secant squared times secant squared is secant to the 4th. So when I factored and simplified, that whole thing turned out just to be secant to the 4th of theta. Another important thing to be able to do is trig substitution. This is going to help you in higher level calculus. So let's do an example. If I wanted to take the square root of 25 minus x squared and write it as a trig expression, but I'm telling you to replace x with 5 times sine of theta. Keep in mind there's this minus in here. That prevents us from being able to distribute this square root, saying that's the square root of 25 minus the square root of x squared. So we cannot do that because of that minus sign. So I'll take this x and replace it with 5 sine of theta. 5 sine of theta squared is 5 sine of theta times 5 sine of theta, which gives me 25 sine squared of theta. Again, I can't distribute this radical right here because of this minus sign. But these both have a 25, so I factored a 25 out, and I am left with 25 times 1 minus sine squared of theta. What is 1 minus sine squared of theta? It's cosine squared of theta. Now that I got rid of that minus sign, I have the square root of 25 times the cosine squared of theta. I can take the square root of 25 to get 5. I can take the square root of cosine squared to get cosine, and this simplified down to just 5 cosine of theta. Another thing that we can do in trig that's very similar to algebra is solving trig equations. You're going to solve trig equations just like you solve algebraic equations, except in algebra you isolate the variable. In trig, you're going to isolate the trig function, and then once you can do that, you can find the angle that makes it hold true. So if you have just one trig function, you can isolate the trig function. If you have more than one trig function or higher powers, then you'll have to do what you did in algebra, where you get everything on one side of the equal sign, 0 on the other, factor, and set the factors equal to 0 to be able to isolate those trig functions. So let's look at this first example. 2 sine of x equals negative 1. Let's isolate the trig function, in this case, sine of x. So I'll divide both sides by 2, and I get the sine of x is equal to negative 1/2. So now we can solve for x, and we can say, okay, where is the sine equal to negative 1/2? Well, the sine is negative in quadrant 3 and in quadrant 4. And the angle in quadrant 3, where the sine is equal to negative 1/2, is 7 pi over 6. But that's not the only angle, right? Remember, trig functions and coterminal angles are the same. So it's not just 7 pi over 6, it's 7 pi over 6 plus any coterminal angle. Remember how we get coterminal angles? We just add and subtract 2 pi multiple times. That's what this plus 2 pi n for n an integer. You can add 2 pi n times, whether it's 1, 2, 3, 4, 5 times, negative 1, negative 2, negative 3 times, whatever. But sine is also negative in quadrant 4. So the angle in quadrant 4, where the sine is equal to negative 1/2, is 11 pi over 6, plus any coterminal angle. So when we're solving trig equations, sometimes we're looking for all solutions, like this example here, but sometimes we're just looking for the angles on one rotation around the unit circle, like this one here. What this is saying is I don't want any coterminal angles. So I'm starting at 0 and including 0, and I'm ending at 2 pi but not including 2 pi, because 2 pi is coterminal with 0, and I'm trying not to include any coterminal angles. So we'll do the same thing. Isolate the trig function. Cosine of x minus 1 equals negative cosine of x. I'll get the cosines together, so I'll add cosine to both sides. That gives me 2 cosine of x minus 1 equals 0. Add 1 to both sides and then divide by 2. So where on one rotation around the unit circle is the cosine equal to 1/2? Well, the cosine is positive in quadrant 1 and in quadrant 4. The angle in quadrant 1 is pi over 3, and the angle in quadrant 4 is 5 pi over 3. All right, let's look at another example. 3 times the tangent cubed of x equals the tangent of x. Get everything on one side of the equal sign, 0 on the other. Factor and set the factors equal to 0. Well, if you see, you got a tangent in common. That's the greatest common factor. So we pull a tangent out, and then we have tangent of x times 3 tangent squared of x minus 1. Set tangent of x equal to 0. Set 3 tangent squared of x minus 1 equal to 0, and solve separately. Tangent of x equals 0. We talked about this when we graphed the tangent, and we said where is the tangent equal to 0? Where the sine is equal to 0, and that's going to be at 0 and pi. Here, 3 tangent squared minus 1, add 1, divide by 3, plus or minus the square root of 1/3 is positive and negative square root of 3 over 3. So I need to know where is the tangent equal to positive root 3 over 3? That's going to be in quadrants 1 and 3. And where is the tangent equal to negative square root of 3 over 3? And that's going to be in quadrants 2 and 4. And those angles are going to be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Secant to the fourth of theta minus 3 times secant squared of theta minus 4 equals 0. Everything is already on one side of the equal sign. 0 is on the other. And so now we just need to factor and set the factors equal to 0. That'll factor into secant squared minus 4 times secant squared plus 1. Set each of the factors equal to 0. Secant squared minus 4 equals 0, and secant squared plus 1 equals 0, and solve separately. Here, we'll add 4 and then take plus or minus the square root. So we can see that your secant is positive and negative 2. Well, sometimes we don't know right off the top of our head where the secant is equal to 2 or where the secant is equal to negative 2, but we do know where the cosine is equal to 1 over 2 and where the cosine is equal to negative 1 over 2. And those angles are going to be pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. For this other factor, secant squared of theta plus 1, subtract 1, then plus or minus the square root, but the square root of negative 1 is non-real. So what does that mean? That means we get no solutions from that factor, and that's okay. So there's only 4 solutions that make this equation hold true. Here we have secant of x times cosecant of x equals 2 secant of x. Get everything on one side of the equal sign, 0 on the other. So I'll subtract 2 secant of x from both sides. Notice they both have a common factor of secant, so we pull the secant out, and we set the factors equal to 0. Secant of x equals 0. Where is the secant of x equal to 0? Well, from when we talked about the graph of the secant, we saw that the secant is never equal to 0. Remember, the secant is the reciprocal of cosine. So if secant was equal to 0, then cosine would be equal to 1 over 0, which is undefined. So we talked about that when we talked about graphing the secant. We said it can never touch the x-axis. So that's because the secant's not equal to 0. So we get no solutions from that factor. Here, cosecant minus 2 equals 0. That gives us that the cosecant is equal to 2. If you don't know where the cosecant is equal to 2, well, that means that the sine is equal to 1/2, and that happens at pi over 6 and 5 pi over 6. Let's look at this last example. 2 cosine squared of theta equals sine of theta plus 1. Now, if we get the sine and the 1 on the other side, and we have 2 cosine of theta minus sine of theta plus 1, we won't be able to factor because the squared term is a cosine and the middle term is a sine. So we're going to have to figure out something better to do here. Do we know a way that we can write sine in terms of cosine or cosine in terms of sine? And the answer is we do, as long as it's squared. Using sine squared plus cosine squared equals 1, we can manipulate that. So this cosine squared is equal to 1 minus sine squared. So then I can distribute the 2, and I have 2 minus 2 sine squared of theta equals sine of theta plus 1. Now I can subtract the sine of theta and subtract the 1, and that's going to give me negative 2 sine squared of theta minus sine, and then this 2 minus this 1 gives me this 1. My next step is to factor, though, and I don't like factoring when the leading coefficient is negative, so this is a perfectly balanced equation, and you can do whatever you want to an equation as long as you do it to both sides. So I'm going to multiply both sides by a negative 1. So when I distribute that negative 1, that becomes a positive 2 sine squared of theta plus sine of theta minus 1 equals 0 times negative 1 is 0. So now this is going to factor into 2 sine of theta minus 1 times sine of theta plus 1, and I can set those factors equal to 0. 2 sine of theta minus 1 equals 0, add 1, divide by 2. Where is the sine equal to 1/2? Pi over 6 and 5 pi over 6. Here, sine of theta plus 1 equals 0, subtract 1. Where is the sine equal to negative 1? At 3 pi over 2. So there are 3 angles that make this equation here hold true. That's it for these trig notes, and I'll see you when we start talking about calculus at trig.